video for unit 3.11 about electronic music. So with electronic music, as we've been doing before, we'll go ahead and identify the part of the source that is the excitation that's supplying the energy. And in this case, that is electricity that's flowing through the wires, through your computer, all those things. Then we have what is doing the oscillating, what is making the partials that are in the spectrum, and that is an electric circuit. And then that spectrum that's generated by the oscillator can go through filters and be different things changed on it, and those are also electric. And then the radiator, itself will always be a loudspeaker, whether that loudspeaker is in your computer or your earbuds or an amplifier. The sound will be coming from a loudspeaker. Okay, so I'm going to go ahead and start by talking about the oscillation. How do we set up the source? Okay, so where does an electronic sound come from? There are, and this is Roman numeral number 3. I'm going to do it in a little different order to see if it makes more sense than in the order, or helps you hear it a different way than what we went through in class. Okay, so for the source oscillation, there are actually 3 ways that you can generate the sound, okay? Number 1 is additive synthesis. Okay, and then this is where you add up sine waves of different frequencies and with different amplitudes. Okay, you did this for the learning activity. Let me find it. Where you played with this Fourier synthesis applet or interactive simulation, where you added a certain amount of frequency 1, a certain amount of frequency 2, a certain amount of frequency 3, and then you saw what the sum or the cumulative, the addition of all of those was. So the trick with additive synthesis is that it requires a lot of inputs. And so for input, you need a amplitude for every frequency. Okay, so it's like you're building up your spectrum one at a time. So you would say, okay, I'm going to have this much of frequency number 1. So over here on your time waveform plot, that would be like, okay, this is a certain amount of my first frequency. Make it a little longer so you can see better. And then I'm going to, so that would be frequency 1 at amplitude number 1. And then second, I'm going to add this much of frequency number 2. We're going to assume these are harmonic right now. So that means that it would, it's less, so it has to have a lower amplitude. So that would mean something like, oops, got off on my line there. Something like gets added in. So that would be amplitude 2. And then you would have frequency number 3. Okay, and then that would be even smaller. 1, 2, 3, something like that. And then you sum all those up to get a complicated wave. Okay. All right, so that's additive synthesis. And the main drawback is that there's lots of amplitudes or lots of inputs, and it would take a while to build up because you'd have to do that for every note, right, that's being played in the song. Okay. Number 2 is called subtractive synthesis, and that is what is used more often, okay, in synthesizing sounds. And that is you start with a complex wave, okay, like a square wave, which has odd harmonics, or a sawtooth wave that has all the harmonics. And then, as the word subtractive would suggest, then you subtract out parts. Okay, there are multiple ways to do this. This goes to the first thing on your handout, this idea that there are some things. So there can be operations to subtract things from the time envelope or add things to the time envelope, but it's modifying this wave, okay? So that might be, well, actually I want to do that right now. Okay, the biggest example of this is filtering. And we talked about low pass filters, high pass filters, and band pass filters. Okay, an example of subtractive synthesis was made by our student in our class this semester about how he used the oscillator part of his program to do some filtering. So in this case, you can see starting with a sine wave. So at first it was a sine wave. Back there. Okay, it was just a sine wave. So here on the bottom left is the spectrum. Okay, here on the white box is the waveform. And this running bar across the top is showing you what kind of signal it is. So starting with the sine wave. And then when the sawtooth wave came on, notice that it is, they are harmonic partials. It's just this is now on a logarithmic scale. So that's why they don't look evenly spaced, but they are in frequency. The triangle wave has, okay. And then triangle we don't really worry about in our class too much. So here's a sawtooth. The sawtooth wave has all of the harmonics. If you add up all of the harmonics in that, with those ratios, with those amplitudes, you get this wave. Or you can just start with this sawtooth wave and then do subtractive synthesis. And then now here is a square wave. And odd partials with that certain amplitude. Okay, so that is the example of the oscillator, like the base signals that you could start with. Okay, and then he goes and applies filters to them. Okay, so this is a song, and now he's going to apply a low pass filter. Okay, this blue line is showing the cutoff frequency and how he's changing it. So you can see we have these complicated sounds, and then he's low pass filtering so that frequencies above that 600 hertz mark don't get through in this case here. And then it's going to go back to the original sound by increasing the cutoff of the low pass filter. Now he's going to do the opposite with the high pass filter. The cutoff of the high pass filter is not up to 600 hertz, and you could hear the tone of frequencies below 600 hertz are not passing through. Now he's going to go back to the original and then show a band pass where both the high frequency cutoff on the left and the low frequency cutoff on the right are changing.
Sat there praying that one day he'd hear me.
So that's an example of subtractive synthesis. That was using the filters to modify the phrase. Now, there are also time-based effects that you can do. Okay, so in this case, this is just a synthesized guitar sound. Okay. Now this next part, he's going to add a delay, which is where he adds basically an echo, repeats the strum. Okay. And now this flanger is a different time domain effect, where he's modifying that time envelope to give that different sound on the attack. That's about the level. You can also watch this whole video without me talking over it if you would like. Okay, and now we're going to look at the reverb, because this is another way you can modify the signal in the time domain. Okay. So this sound has the option of making it sound like a different space by importing the impulse response from a different building, and from like a church in that example. Okay, so in subtractive synthesis, you start with a complex wave and then you filter out the frequencies. Okay, all right. And examples of this. Okay, now this is Roman numeral number 2. Okay, examples of subtractive synthesis that you can do is if you start with a square wave and apply a low pass filter. What is the spectrum going to look like? The spectrum is going to look like, these are my, equally spaced. It's going to have just the odd partials, but then only a few of them. It's not going to go on very long. I have added a low pass filter. And so the question on the handout for Roman numeral number 2 is, what instrument would this sound like? Okay, so the way you know that is you say a square wave has odd partials. Sorry, odd harmonics only. Okay, and that was most like, that is the same as an open closed tube. And the open closed tube model was a good model for which instrument? The clarinet. Okay, so you have to make sure that the sound you're trying to generate with subtractive synthesis has starts with the same partials as in your final sound. The low pass filter is then applied because a clarinet is a very warm, mellow instrument typically, and so you don't run a lot of high frequencies. Okay, well, what if you start with a sawtooth wave and apply a bandpass filter? Okay, so in that case, those are not evenly spaced. Pretend they are evenly spaced. I'll try again. Oh, goodness. Okay. And then it would have all of these harmonic partials, the initial sawtooth wave. Okay, so sawtooth waves have all partials, harmonic partials. Okay, and all harmonics was a good model for the bowed string instruments. Okay, so this is separate from the specific case we're doing right now. Just sawtooth waves would be a good generating oscillator for bowed strings, air jet, so our open pipes like flutes and organs, and also for our brass or lip reed instrument. And also for the mechanical reeds that are not the clarinet, because they have that conical or cone-shaped cross-section. Okay, all of this is listed on the 3.1 handout, summary of all of these characteristics. Okay, so sawtooth wave would like that. Okay, so now if we apply a bandpass filter, it might be something like this. Oops, we were making them more square. Okay, then it would cut off some of the high frequencies, maybe some really low frequencies. So this example of the sawtooth wave with one bandpass filter would be an example of a flute or other brass/lip reed instruments. Okay, but for bowed string, you would not want to use just one bandpass filter. You still do want to start with a sawtooth wave, because you need all harmonics, right? But the bowed string instruments have air and wood resonances. So they have like two formants if we're thinking about it in terms of the voice, right? So you have to actually have like two peaks, not just one. So if you start with pretend they're evenly spaced again, kind of a sawtooth spectrum, instead of just doing the one bandpass filter, you would need one that was kind of around the air resonance and another that's around the wood resonance or something like that. That's not exactly what it looks like, but it's the idea. So you need a two bandpass filters around certain frequencies to simulate the air and wood resonances. Okay, these are examples of subtractive synthesis because you start with a complex wave and then you are removing things as you go along. Okay, so that was Roman numeral number 2. Okay, going back to Roman numeral number 3, we had additive synthesis, where you added up the sine waves. You have subtractive synthesis, where you start with a complex wave and you remove things. Okay, and now number 3 is called sampling synthesis. Okay, now in number 3, there are pre-recorded samples of real instruments in real spaces, okay, of live sounds. Not that the other aren't real, but pre-recorded live sounds. So you would have, if you wanted a piano, you would have to record a piano playing every note on the piano, usually at different loudnesses, so that you capture that change in tone color. This is extremely common with percussion instruments because of their very rich spectrum full of inharmonic partials. So they're harder to build, like with the sampling. So you start with white noise, but it's still quite tricky to build up those sounds. So especially percussion sounds often are pre-recorded samples of live sounds. So you can, in sampling synthesis, you are selecting from pre-recorded samples. Okay. And then number 4, the fourth kind of electronic way or computational way to generate a signal is called simulation synthesis. Okay, in simulation synthesis, you basically build a computer or mathematical model of the physical processes, like the fact that it's an open-closed tube or an open-open tube, okay? But you try to simulate the effects, the physical effects, like the opening and closing of the vocal folds if you were doing speech, right? And then sending it through a vocal tract that's made up of those little concentric little discs of different cross sections. So you're trying to simulate all of the effects, the flow of the air or the vibration of the string. You're trying to build that up. Okay. Now all of these definitions, just so you remember, are in the slides. Okay, so that you can have them as well there. Okay. All right. So that kind of takes care of items 2 and 3 on your review. Okay, before I forget, let's go back up to the top of the handout. There is this thing that talks about filters on the spectrum and the time waveform, modifications to the time waveform. So filters on the spectrum would be your low pass filter, your high pass filter, and your band pass filter are examples of things that act on the spectrum. Okay. Other things that modify the time envelope. Okay. Or the time waveform would be things like echo, delay, and reverb. And then also just that any changes to the attack or decay. So let's take a minute and talk about what I mean by the difference between time waveform and time envelope. Okay, so if this is my time axis, my wave is coming through. Let's say I have some wave. Okay, probably not that spiky, but you get the idea. Okay, so that would be a signal. Okay, so certain kinds of things you could do, right? One would be peak clipping, right? Peak clipping is an example of a modification to the time waveform that would introduce distortion, because you would have a whole bunch of high frequency components coming about whenever these waves get cut off because of the peak clipping. Okay. Can do another one that's illustrated by Alex in that video, where if this is your wave, you actually chop it a different way and you take out all the things in the middle. So it's like you zero out all of that part. So then your wave now just goes. And it doesn't do, it just goes to 0 in between. Just drops straight down to 0. Pretend it's all of the things I had tried to bold were outside of those green lines. That's what I mean to say. And in between, it's just 0, just jumps. Okay, that would be called center clipping. Okay. Let's see, what would reverb essentially do? Okay, if I had my sound and there was some attack and some sustain and then a decay, okay, this would be the time waveform. The time envelope, I should want to use this guy. Looks like this. There's the attack, the sustain, and the decay. Only driven instruments will have sustain in real life, but in electronic music, you can do whatever you would like. Okay, so this pink one is called the time envelope. It kind of traces out the peaks of the time waveform. Okay. So an example of a modification you could do would be to add reverb. What that would do would be to change the decay. Basically make the sound last longer. So instead of that decay, you might say, I want it to go for a really long time. That would change the envelope, which would then change the wave so that it just kind of died out for a longer time. Okay. So that's an example. With echo, you would basically be taking that same waveform and then adding it in a little bit later. Right. So there's all sorts of things. Anything that modifies the time waveform or the time envelope is a different kind of modification. Okay, now I think we can go on to Roman numeral number. I may be off on my numbers. This one may have been number 1. Sorry. Okay. Number 2, or what I'm calling number 2 at least, is the one that asks for definitions of oscillator, envelope, controller, filter, and MIDI. Okay. These definitions are written out nicely in the slides. Right here. They are also written out in words on the question number 1 on the back. So we will try to go through them here and give examples. Okay, so the oscillator, that's what we were talking about at the beginning. Okay, the oscillator generates the wave. And that can be via additive synthesis or sampling synthesis or subtractive synthesis or simulation synthesis. Okay. Okay, then there is typically an envelope that's applied, right? That's the modifications in the time domain. Or you could say that it sets the time waveform. Okay. The attack, the sustain, the decay. All right. Then there is the controller, which is basically controls all the inputs. These are the simple words. We'll go to the more official words here in just a second. Okay, and then the filter modifies the spectrum of the sound. And then there is MIDI, which is the computer language used to communicate between components. Okay, you might have heard of a MIDI keyboard. That would be a keyboard that would plug into your computer and communicate with the electronic music generation software. There are other MIDI instruments, and all of those. Okay, so let's look at the handout now, specifically to this question number 1, because this is written out a little nicer than what I just did before. A time-varying function often used to control the amplitude of a waveform is the envelope, or an envelope generator. Yeah. The electronic device used to vary the parameters of a synthesizer in real time is the controller. Electronic device that modifies the spectrum of a complex tone will be a filter. The electronic device that generates the waveform is the oscillator. And the protocol that enables musical devices to communicate with each other is called MIDI. Okay. All right. Well, hopefully that's helpful for getting all of this straight. I do recommend that you watch the repronunciation video that I will also post with this.